Okay, good. It's a pleasure to introduce our next speaker. Andreas Pithis is going to tell us about group field theory and spin-form renormalization. Andreas.
All right. So first of all, I would like to thank the organizers for this nice conference, the very nice dinner that we had last night, and for the kind invitation for me to talk here to you. This is quite a privilege, and I really appreciate this. I would also like to thank my dear collaborators, some of whom are here in the audience today. So I was asked to speak about spin-form renormalization from the GFT perspective. I hope that at least to some extent I can live up to this request. It's not so easy because I'm not a spin-form practitioner. So I hope I'm not going to generate too much confusion by dwelling too much on the GFT perspective. So as I've said, this talk is about GFT, its connection to spin forms and the renormalization thereof. And in particular, what we can learn about that for the continuum limit of the theory. So my presentation is obviously, due to time constraints, limited on certain things that are going on in the field, and also biased personally because I have my preferences. Okay. Okay. Good. So the rough structure of the talk is I will speak about GFT in connection to other approaches, namely spin forms and tensor models, where GFT originates from. And then I come to GFT renormalization. So I have to speak about power counting, perturbative and non-perturbative renormalization, and the recent Landau-Ginzburg mean field theory application to GFTs. And I will close with conclusions and an outlook. So what is group field theory? So this picture is not meant to indicate any kind of hierarchy or so. It's a way to see GFT from the point of view of GFT, namely that it sits at the confluence of different approaches to quantum gravity that seek to provide a lattice regularization of the quantum gravitational path integral. And GFT has drawn over the last decades from these approaches and has grown. And this talk will focus on the relations to spin forms and tensor models. So what are spin forms from the GFT perspective? So GFTs are a tentative completion of spin-form models, and I'm emphasizing here that it's a tentative completion because there are other attempts apart from GFT that try to seek a completion of spin-form models. We've seen, for instance, the presentation of Seth earlier this morning that deals with another approach to do so. So what are spin-form models? They provide to seek to give a lattice regularized quantum gravitational path integral in the sense of a sum over histories definition. And one quantum history therein corresponds to a spin form. And then for this spin form, you have to specify the class from which the complex comes from, the complex itself, of course, and then the algebraic data which dresses this complex. And the basic component in this spin-form model is given by the quantum amplitude for this given complex that you've chosen. So Z of gamma, where gamma is this spin-form graph, is the sum over the product of these amplitudes, the phase, edge, and vertex amplitudes. And as indicated here with this with J and I is the algebraic data that addresses this structure. So most work usually focuses on working with one single simplicial complex graph. And while we know that, for instance, looking at earlier works and then also this previous talk, that radiative corrections drive us out of the simplicial class because we are looking at melonic contributions, for instance. And also when we have a single complex, then this suggests seemingly that there is a finite number of degrees of freedom when we might expect that quantum gravity is in fact a theory of an infinite number of degrees of freedom. So we need maybe a little bit more. Namely, we need a set of all quantum amplitudes for all spin-form complexes and an organizational principle for the amplitudes. And GFT can provide this for us in the sense that it provides a QFT generating function for spin-form amplitudes. In the sense that the perturbative expansion of group field theory or particular model is a spin-form model with a sum of our complexes, as indicated here. So you have a weighted sum, and GFT provides the weights for this, and here's the Feynman amplitude, or your spin-form amplitude for the respective graph, gamma. So we would like to compute in full glory this partition function, but if we want to do this, then we also have to consider the renormalization thereof, and we have to understand what kind of radiative corrections pop up. If we renormalize, we would like to reabsorb them. So in the end, we would like to compute, hopefully, a renormalized version of this thing, and the total evaluation of this object would allow us to have access to the continuum limit. So now that I've spoken a little bit about the relation to spin-form models, I speak a little bit about the relation to tensor models, because GFTs are in fact algebraically enriched tensor models. And how do you motivate tensor models? By going to lower dimensions and to understand them as a generalization of matrix models, which provide a success story, in fact, for 2D quantum gravity. So here I'm flashing a standard action for a matrix model, and here the graphical representation of the propagator and for the interaction term. And here's the partition function. So the Feynman diagrams of such a model are stranded diagrams, and they are dual to tessellations of closed surfaces, as well known. And this is due to the rigid interplay between combinatorics and the global structure of Feynman diagrams. And then it's also well known that the large N expansion is indexed by the genus of the closed surfaces that we are triangulating. And the free energy here as a sum over these amplitudes, the weighted sum, can be rewritten in such a way. So this sum is dominated then by genus zero surfaces. And from the non-analyticity properties of this object here, we obtain the critical exponents and the continuum limit. And the one is, that is only lately really rigorously apparently shown that the continuum limit of this model is equivalent to 2D Euclidean Liouville quantum gravity. So the question is how to generalize this when we go to higher dimensions. And initially, one worked with plain tensor models without this additional combinatorial degree of freedom called color that was introduced later on by Gurau and also others, which allows us to ensure nice global properties like manifold structure. So I'm flashing here standard action for such a colored tensor model. And at rank 4, I'm writing down here the kinetic term and the interaction term. And the identification of a tensor with a tetrahedron in this approach is ad hoc. And then you have here the interaction term, which has the combinatorics of a 4-simplex. And I'm indicating here the colors, so that the Feynman diagrams, in fact, are edge-colored graphs with quite a rigid combinatorics, so that they are dual to discrete orientable manifolds. And then you can play the game of providing the large N expansion, which is then indexed by a higher dimensional analog of the genus G. So omega, called the Gouraud degree, which is not a topological invariant. And you see that the sum here, which looks rather similar to what you have for matrix models, is dominated by those contributions with degree 0, which are the melonic diagrams. And then again, from the non-analyticity properties of this, you find information about the continuum limit. You can play the game also for what is known now as uncolored models, namely you have your simplicial model and you integrate out all but one color, and then you get to a tensor invariant model, which has an interaction term, which is an infinite sum over even powered potentials, and that is invariant with respect to unitary or orthogonal transformations. So the continuum limit of these models is mostly that of a branched polymer phase. And I'm saying here for such simple models, even though they are, of course, already pretty involved. So, and with mostly, I mean that there's been some work which tries to get out of this universality class, and one gets to the planar phase, but still it's lower dimensional and it's kind of undesirable. So in this approach, it's an open problem to find non-trivial metric spaces with dimension larger than 2. So having motivated now this, the question is, okay, what's group field theory? So as I've said, the Feynman expansion of tensor model generates random discrete geometries, and GFTs are enriched tensor models in the sense that they are QFTs of tensor fields living on specific Lie groups. And for what is interesting us, G is the local symmetry group of space-time. These theories are amended by a closure condition, and they are specified by a combinatorial non-local interaction, so that the Feynman expansion defines a lattice gauge theory on a random lattice as a completion, tentative completion of spin-form models. And as an added bonus, you can use now quantum field theory concepts and methods to extract information about renormalization and mean field analysis, to unravel their phase structure, and also to extract physics like cosmology and black holes. And with that here in particular, I'm referring to Ed's and Daniele's talk, and in the afternoon, there are talks by Alex and Luca on the cosmology application of GFT. So coming to the first point, you have here your group field on R copies of the Lie group G, and they're taking values then in the real or complex numbers. One typically assumes that these functions are in fact L2 functions, and these group elements here are in fact parallel transports. So you can construct a phase space, and you can construct then the dual formulation on the momentum space, where the dual variables are the fluxes. And then in this way, it's maybe more transparent to see that the closure condition as imposed by a group averaging, then on the level of the momentum space is a closure of the fluxes, so that in fact this structure here closes to form a tetrahedron. Now, as I said, they are specified by combinatorial non-local action. So this is just symbolic here. So a particular model is specified by the kinetic operator, by the interaction term, and in particular by the group, the rank. and the symmetries of the field. And then the choices of the kinetic and the interaction term specify then your phase, edge, and vertex amplitudes of the respective spinform models. So famous examples are, for instance, in 3D, the Bulatov model, as is well known, which has the combinatorics, the interaction term has the combinatorics of 3 simplex. And then in 4D of the Oguri model with the combinatorics of 4 simplex. And you can also write down the colored versions of this, as was done by these gentlemen. And they have a more well-behaved expansion, as you've seen already in the case of the tensor model, so that the discrete geometries that they generate are in fact dual to pseudo-manifolds. And you can play the game also again for the uncoloring such colored versions thereof, so that you get your tensor invariant interactions, for instance, melonic contributions, necklaces, and so forth. So this is done so as that the Feynman expansion defines a lattice gauge theory on a random lattice. The expansion is weighted by amplitudes of specific lattice gauge theory with structure group G. So I'm just flashing this here, and this is, I mean, of course, what you've seen already at the beginning. So you have here a weighted sum over these amplitudes, which are your spinform amplitudes. But now it's maybe, I'm already indicating this here, that the class of graphs that we're summing over is not only the simplicial class, but also goes beyond by looking at cellular complexes. So typical applications of this formalism are then, as you saw before, the one of Bulatov and Oguri, so that provides GFT quantizations of BF theory in 3 and 4D. And when you are, for instance, in for rank 4 fields and the group is SL2C, and then you add simplicity constraints, you get to quantum gravity amplitudes. In particular, I mean, for the Barry-Crane model, for the EPRL model, and other spinform models. Another interesting example is, of course, the rank 3 case with G is equal to SU2, so that you're working, for instance, with the Bulatov model, and that gives rise to the Ponzano-Regge state sum model to quantize 3D Euclidean quantum gravity. So now that I've spoken a little bit about the motivation of GFT, what do we know about its renormalization? So GFTs suffer from divergences similar to local perturbative quantum field theories. And these divergences arise from short-scale structure of the configuration space, so the Lie group. So they are more difficult to treat because of the non-locality of group field theory interactions. And they must be regularized and renormalized for the consistency of the quantum theory. So I hope it has transpired so far that given the relations of GFT and spinforms, that when you look at GFT renormalization, you're also dealing with spinform renormalization. And that when you set up renormalizability criteria, this also informs us about model building. In this way, we would like to, I mean, via renormalization, we would like to get access to the phase structure and continuum limits. And suffice to say that a lot of the studies that have been done over the last decade focus on groups like U1, SU2, or R. And recently, we are going beyond this by looking at models with SL2C, for instance. So that's to say that we are slowly moving step by step towards renormalizable models for 4D quantum gravity. So strategies to inform ourselves about the GFT renormalization are two paths in principle that have been pursued. And the first path I'm just flashing here. So you introduce a heat kernel with a cutoff, so to study the large N behavior of group fields, group theories, in particular for the Bulatov-Oguri type models. You see that then they are dominated by melonic diagrams. that topologically singular spin-foam structures are convergent. And beyond leading order, the critical properties and continuum limit are not so well understood. Now, when you go to the second part here, which is the focus of the remainder of this talk, you can use the full machinery of GFT renormalization. As in ordinary QFTs, you have to define a notion of scale to set up mode integration. And this is done via a non-trivial propagator in the action, so Laplace operator on the group. And maybe I should mention here that for me then, if I'm looking at the Laplacian on group, that large representation labels are for me the UV, and small representation labels are the infrared. So you have to start with a power counting analysis to determine the degree of divergence of graphs that you are generating in your GFT. And you can say something about perturbative and non-perturbative renormalization. And I'm coming then in the end to the application of Landau-Ginzburg mean field theory to this class of theories. So GFT and power counting, we would like to understand how the Feynman diagrams diverge in the ultraviolet. So you have to determine the superficial degree of divergence, which captures this UV behavior, and I'm flashing this here. And this degree of divergence, omega, is more complicated as for local scalar field theories. And for power counting renormalizability, you have to demand that the degree should be bounded from above. So from this understanding, you can derive criteria of renormalizability. And this was pursued by these people here, that a full classification of renormalizable melonic GFTs with closure was given, or were given. One focuses on melonic diagrams since they are most divergent. So this degree of divergence, which I'm not writing down here explicitly, depends on the number of faces of your graphs. And melonic diagrams maximize the faces in these diagrams. Okay, so that's why one mostly focuses on the melonic diagrams. And that's why they are most divergent, yeah. And so one has given a general abelian power counting theorem, and for non-abelian group that. So, and I'm flashing here this table, which I've stolen from Sylvain's very nice review on this matter from 2016, where he groups models that have been analyzed using power counting analysis. And you see here that this degree of divergence is really a complicated object, which depends on the number of propagator lines, number of interaction vertices, external lines, and so forth and so forth. And the upshot is that UV divergences arise from subgraphs and are absorbable in tensor invariant effective interactions. And this can be seen as to correspond to coarse graining of the lattice. So once power counting renormalizability has been checked, we would like to study the running of couplings in our model. And we would like to check for the convergence of the running of this coupling in the UV and in the IR. So in principle, the two main motivations of renormalization group investigations are then to check whether the theory is consistent in the UV and in the IR. So, for instance, we check for the consistency of the theory in the deep UV in a perturbative scheme. And when the couplings there converge to zero, the theory is described by a Gaussian distribution. And this is what we understand as asymptotic freedom. If this doesn't happen, then we have to study the theory space away from the perturbative fixed point and check for the consistency of the theory in a non-perturbative scheme. And if the couplings converge there to non-zero values, then the theory is non-Gaussian and you have asymptotic safety. And this corresponds to non-trivial fixed points as UV completion of the theory. So, and now you can also look at the IR behavior, of course. look there for fixed point, phases, and phase transitions. And the reason why we, or like I, am interested in studying the IR behavior in particular of GFTs is because infrared fixed points, in our point of view, they correspond to continuum limits of the theory. So you flow to the IR, that means to small representation labels, and you find something like a condensate phase. Then a condensate phase is something that is occupied by a lot of quanta, or maybe infinitely many, depending on the domain you're working with, of course. And if you have many quanta and they are labeled with small representation labels, so like small j, small rho, depending on whether you work with the EPRL or Barry-Crane model, means that your tetrahedra are small. And if you want to model something smooth, I would rather say I want to do this with many quanta and they are small. They're coming together. So these goals can be addressed using functional renormalization. Of course, you can use other schemes, I mean, to analyze the perturbative and non-perturbative aspects of renormalization, but this tool is quite powerful and you can do all of this with this method. So here I'm flashing the bare ingredients of this method. So you have the renormalization group scale K, and just to mention that in the context of GFTs and spinforms, the scale is not related to an energy scale. Yeah? So as I've said, it relates to the representation labels. Then you have the scale-dependent partition function and the generating function of connected diagrams. And from this, using the regulator function, which allows you to eliminate modes, depending on whether you go to the IR or UV, you can construct the scale-dependent effective action. So to figure this in this picture is you're defining, for instance, an action in the UV, and you would like to know how it morphs into another action towards the IR. And this morphing procedure, if it works out and you come here to a fixed point in the IR, then this means that you're actually renormalizing the distribution, the probability distribution that is defined herein. So this is differentially implemented using the Wetterich-Morris equation that was introduced for continuum fields, and that has successfully been transferred to GFTs, matrix, and tensor models over the last 10 years. So from this equation here, you obtain your set of beta functions for the running of the couplings, and you only get a consistent set of equations for dimensionless couplings. So you have to rescale dimensionful couplings with powers of the RG scale, and the precise rescaling is inferred from the superficial degree of divergence that I flashed in the power counting part of the talk. So just indicated here. And the set of beta functions vanishes at UV and IR fixed points. So the challenges for the application of this machinery to GFT really lie in the combinatorics. In particular, as you were told a few slides ago by me, the superficial degree of divergence is a complicated object because it depends on the non-local combinatorics. And that gives rise to a complicated structure of the beta functions, which are typically non-autonomous. So it's hard to check the convergence of fixed points, and also since you have at a, let's say, quartic order or sextic order or so of a truncation that you're choosing, you have quite a lot of possible interactions depending on the interaction that you are choosing. Yeah, for instance, a melonic necklace at order 6 and so forth. And you have all to incorporate them into your beta functions, and you would have to go to higher and higher orders, so that the calculations become very fast, very complicated. Nevertheless, there are interesting results, which depend on the rank of the GFT field, the group dimension, and the interactions. studied that in the deep UV and the IR, the beta functions become in fact autonomous, so this is nice. And that in the deep UV, you find models with asymptotic freedom and asymptotic safety. In the deep IR, if the Lie group on which the group field lives is non-compact, then this gives rise quite generically to condensate phases and phase transitions. So this is nice because, in my opinion, this informs us about possible continuum limits of such models. So on the next slide, I'm going to just flash the application of this method to a rank 4 model living on SL2C. And we impose simplicity constraints a la Barrett-Crane. And the building blocks, your fields, are space-like tetrahedra. So we're working here with a cyclic melonic interaction. In principle, this is a sum of ever more getting complicated chain of melons. But we could also use some other tensor invariant interaction. And this gives rise to here your Wetterich-Morris equation. And the interesting thing that you see here, so this is work in progress, by the way, is that the right-hand side of the Wetterich-Morris equation vanishes due to the regulator structure of your theory on SL2C. So what does this mean? That in the IR, there's only a Gaussian fixed point. That means the theory becomes asymptotically free. And I believe that even if we worked with EPRS simplicity constraints, this would be the same result, because we are working with a regulator function on SL2C, which doesn't really know about the simplicity constraints. So this is nice. So you're flowing from the UV, so large representation labels, to small ones. And you are finding a very simple phase structure, like one with the condensate phase and one without. And you see that all of the phase structure is clarified at the Gaussian fixed point. So this is kind of resonating with these phenomenological applications of GFT to cosmology. Because there, as you've seen, for instance, in the talks of Daniele and Ed, one is typically working with a non-interacting GFT. And this is kind of here a justification that this makes sense. We don't have to use the interactions in this picture because the theory is asymptotically free in the IR. So I hope it has transpired that the renormalization group analysis of such models is rather complicated. So there's a way to learn something about the phase structure of these models using an approximation scheme, which is very well known in statistical field theory, namely Landau-Ginzburg mean field theory. And what you do there is you compute the this Z in a saddle point evaluation and study the behavior quadratic perturbations around this saddle point. And this gives you this simple phase structure and tells you that around the Gaussian fixed point, the phase structure is clarified. And you would like to understand, or like you can describe with this method, transitions in between the situation where the field expectation value is 0 and non-zero. And this is interesting for GFT because this situation here would correspond to one where you have a lot of quanta residing in low representation labels. Now, to figure this method out from the point of view of Wilsonian renormalization, you would say that the action you're working with in Landau-Ginzburg theory lies somewhere here in between the UV and the IR. And it's a phenomenologically motivated action where all the microscopic details are encapsulated in the couplings of the model and in the order parameter. And then from this action, you compute the equation of motion, you compute your uniform minimizers, phi naught, you linearize the equation of motion in this way, and you can extract, like this is just standard statistical field theory, you extract the correlation function and the correlation length. And then you have to check for the self-consistency of this linearization via the Ginzburg Q, which is this here. So you're integrating over the domain up to the correlation length, the correlation function, and you're dividing over the background contribution. So if this is small, mean field theory can be consistently applied. And the description that it gives of the phase structure is self-consistent. So now we have done this for simple models, but I'm flashing here the results that we obtained for SL2C and Berry-Crane simplicity imposed, and we worked with space-like tetrahedra. And we worked with actions like these here, so tensor invariant ones and simplicial ones. And you see here that the Ginzburg Q is an exponentially decaying function. It depends on the combinatorics of these interactions. And this exponential decay tells us that at criticality, so where there's a phase transition, the fluctuations are 0, and that means the linearization works well and describes nicely a two-phase structure. And this exponential decay comes from the domain that the group field is living on, so SL2C, which is interesting. And you can generalize this to arbitrary interactions. What we have done also is, as in GFT condensate cosmology, add free massless scalar fields on the lattice. You get the same behavior. And the most realistic case so far was that we looked at the colored simplicial model with Berry-Crane simplicity constraints imposed and working with space-like tetrahedra, and the same thing happens there. So the upshot is that the Ginzburg Q always vanishes at criticality, and that means that a non-perturbative condensate phase exists, and the idea is to give this a tentative continuum geometric interpretation. So work in progress is that we extend for the imposition of the Berry-Crane simplicity constraints this to the case where we include time-like and light-like tetrahedra. And we are also working on extending this application here to the case where simplicity is imposed a la EPRL. And I think that we will obtain quite the same result there, meaning the same exponential decay behavior, because of course the EPRL model is an SL2C model. So I'm using this picture here to indicate, okay, what do we know and what do we not know to conclude. So GFT has transpired our tentative completions of spinform models. And when we are discussing GFT renormalization, we are also discussing spinform renormalization. Step by step, we are moving to the analysis of more realistic models. And I hope that it came across that looking at the renormalization of such models, you have a pathway to extract the continuum limit in macroscopic physics. And this relates here to the phenomenological application of GFT to cosmology and black holes, and in particular to the talks of these gentlemen. So the road ahead, open issues. In my point of view, you have to further clarify the theory space, namely the relation between full-fledged models for 4D Lorentzian quantum gravity, that means colored simplicial models with simplicity constraints imposed, and non-trivial propagator, so that means Laplace operator, and the tensor invariant models. This hasn't been done fully. When this is done, one has to extend all of these analysis of perturbative and non-perturbative randomization to these cases and analyze their phase structure. And in particular, what's pressing is to look at the case where you are imposing the EPRL simplicity constraints on these group fields. Then also, if you want to characterize the geometries that you're getting in these condensate phases, I think it would be good to devise observables and tools, so like something like the spectral dimension analog for GFTs, and try to understand how the flow of these operators works out while you move along scales. And then it would also be nice to connect such analysis with FRG application to first order gravities in the continuum, which in the context of the asymptotic safety community to asymptotic safety approach to quantum gravity has only recently been commenced. So with this, I'm done, and I thank you for listening.
Thank you, Andreas, for this comprehensive review. There's time for 2 short questions with comments. 1, 2.
Hello, thank you so much for the very clear talk. I have a very naive question, perhaps a very short one. You say that the GFT is a completion of the Bertrand and now the EPRL model. In what sense do you say it is a completion, like, or a tentative completion? What sense?
So completion was really meant in the sense that, okay, normally you discuss these models as based on a single 4-simplex. And right. GFT gives you the means to go beyond considering just a single 4-simplex.
And one more question is, you took a particular form of the regulator when you were discussing the renormalization. Yeah. Was there a particular motivation of using that particular regulator function?
In principle, these results are supposed to be independent of the choice of regulator function. So we are working with lithium regulating function, but for the results that we have there, that doesn't matter. It's what we obtained there about the asymptotic freedom in the IR. That is just because of the structure of the Lorentz group and the regulating function on this group manifold.
Samart?
Hi, thanks for the talk. It was really nice. And it's also, I guess, a naive question, but, and so I don't know the statistical field theory very well, but it seems like there could be maybe an intuitive or some sort of connection between like phase transitions that you mentioned and, you know, tunneling phenomena that had been mentioned earlier. So is there anything?
Which phenomenon?
Tunneling.
Tunneling phenomenon. Well, I wouldn't understand or know really what tunneling for quantum geometries would mean. I mean, that you could tunnel maybe like if you have a 5 to the 4 potential, or the analog of that for group fields, you could tunnel from one vacuum state to another one. But let's say these kind of maybe kink solutions or so, I wouldn't really understand what it means in the context of quantum geometry. So, but it's maybe an interesting thing to pursue.
Thank you.
Good. Before thanking, don't forget there's a panel today at 2 in this room, and there's going to be an announcement. Don't leave immediately after thanking Andreas.
Thank you.